Okay, so let me talk about this assignment. So, beginning is pretty simple. What's the difference between a scalar quantity and a vector quantity? When in doubt, use the word while. Okay, you could say a scalar quantity has this, while a vector quantity has this. Okay. When you get to number 5, so let's talk about number 5, and there's an important step on number 5 where you have 70.0 kilometers per hour. Now, because we're in the MKS system, you have to convert kilometers per hour into meters per second. I'm going to show you exactly how I want this done. This is the most common conversion we are going to do in this class. Is kilometers per hour into meters per second. I'm going to show you exactly how I want it done. Because once you figure it out, it's the same way every time. Start off with this. The 70 kilometers per 1 hour literally means that. That's how far you're going to go in 1 hour. Okay? Stack it. Okay? Put the 70 kilometers on top, put the 1 hour down below. Okay? Don't combine them. Put the kilometers on top, put the hour down below. I always deal with the kilometers first. 1 kilometer is how many meters?
1,000.
1,000. Okay, if you don't believe me, look on the back of the yellow sheet. You can find the kilo means 1,000. If you stop right now, what units do you have?
Meters per hour.
You have meters per hour. Do you want meters per hour?
Absolutely not.
You want meters per second. Now, there's 2 ways you can do this. You got to take the hour and put the hour up here. Okay, you've got to do that. Now, here's your 2 options. 1 hour is how many minutes?
60.
1 hour is 60 minutes. Then you got to take 1 minute and make 1 minute into seconds, which is going to be 60 seconds. Huh?
Can we just do 36?
That's going to be option number 2. Okay?
Yes.
So your other option is if you don't like doing that in steps, you can just go 1 hour is 3,600 seconds. Okay? Now, here's the shortcut version of this. Because you're multiplying by 1,000 and you're dividing by 36, the shortcut version is actually, you can like lop off zeros. So the shortcut version is that you take that number, you multiply it by 10, and then you divide it by 36. So that's the same step every time. So to convert from kilometers per hour to meters per second, multiply by 10, divided by 36. Now, Vanessa, do us a favor, you've got that calculator out. We haven't really talked about significant digits, but significant digits are a reflection of how good the measurement is. So 70.0, anytime you have a decimal point, all the zeros count. So 70.0 has 3 significant digits. That means when you do this conversion, you need to keep at least 3 digits in this answer. So Vanessa, take 70 times 10 and divide it by 36. What'd you get?
19.4.
19.4. Now, do not round that to 19. Keep it as 19.4. If you can have more digits than that, but you can't have less than that. So, it's going to take Diane 1.75 seconds to type, how are you? So, because she's traveling at a constant velocity, one option is that we can use distance equals velocity times time. The 19.4 meters per second, that's how fast she's going. You have the time, multiply the 2 numbers together, boom, the rocket races. And you're going to use this idea of distance equals velocity times time. You're going to use that on number 5. You're going to use that on number 7. You're going to use it on number 8, number 10, and 11. Okay? So anytime you have constant velocity, you can use distance equals velocity times time. I'll always give you 2 of the variables, solve for the 3rd. Now, let's talk about number 6, because I want to give you a visual of what's happening on number 6. So you've got a rocket, okay? What do you think the initial velocity of the rocket's going to be? 0. Rocket's going to be at rest, sitting on the launch pad, okay? Now, I'm going to fire this thing, and it's going to accelerate at 5 meters per second squared for 8 seconds. Draw this motion on a velocity time graph, labeling the initial velocity and the final velocity. So this has to be done on like graph paper, not here, okay? It doesn't have to take up the full sheet of paper. But you're gonna have a velocity time graph. You're gonna start off at 0, because that's the initial velocity of the rocket, right? Now, think this through. You have an acceleration of 5 meters per second squared. So you're gonna do this for 8 seconds. What does the slope of a velocity time graph give you? Acceleration. Do you have the acceleration?
Oh,
Yes. So you know what the slope of the line is.
no.
So here's the story. At the end of 1 second, how fast do you think the rocket is moving?
5 meters.
5 meters per second. Because that's what that slope represents. For every second that goes by, the velocity increases 5 meters per second. At the end of 2 seconds, you're going to be going
10.
10, 15, 20. Because it has a straight sloping line because we have the same force acting on it. So as long as the same force acts on an object, the acceleration stays the same. Okay, there's no variation on the theme. Now, at the end of 8 seconds, so imagine it's a squirrel rocket. Okay, here's the rocket. Okay, we're going to accelerate it for 8 seconds. Going to go up, 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 up. Now, at the end of 8 seconds, I'm going to shut off the engine. So that's like me throwing the squirrel up in the air. When the squirrel leaves my hand, that's like shutting off the engines. When I shut off the engines, what's the only force left acting on the squirrel?
Correct.
Gravity. Oh, is gravity going to make it slow down?
Yes.
Yes. So here's the story. So initially, you were getting bigger and bigger positive velocities that were pointing upward. I shut off the engines. What happens to the velocity vectors? Do they still point upward? Yes. Because this is after the squirrel leaves my hand. Do they still point upward?
Oh, yeah.
But they're going to get
Slower.
smaller
Smaller.
because they're slowing down. So once I shut off the engines, then the velocity vectors are going to get smaller and smaller and smaller. So when the rocket engines were firing, what was the sign of my acceleration vector? Positive or negative? Positive?
Yes.
And that was 5 meters per second squared. As soon as I shut off the engines, which direction do you think my acceleration vector is going to point?
Nowhere.
Downward.
Downward, because gravity.
Ah, because gravity is the only force making it slow down. So after I shut off the engines, then I'm going to have some negative acceleration. So on your velocity time graph, it's going to go like this for 8 seconds. Then I'm going to shut off the rocket engines. As soon as I shut off the rocket engines, what do you think that velocity, this is a velocity time graph, not a position time graph. As soon as I shut off the rocket engines, what do you think that graph is going to do?
Start going down.
Going to come down like this. Because now I'm going to have negative acceleration, because eventually what's the rocket going to do? Oh, it's going to come back to Earth. What 3 things does it have to do to come back down to Earth? It has to slow down.
Stop and speed up.
When do you think it stops?
When
At its highest
stops
point,
at the highest point.
right? Because that's when the velocity is going to go to 0. So your velocity time graph is going to look something like this, okay? All right, when you get to questions 12 and 13 on the back side, keep in mind that 12 is a position time graph, 13 is a velocity time graph, okay? Keep that in mind. Okay, I'm done. You're on your own. You only have to draw one graph, so I'll cut some graph paper in half and give you just everybody half sheet graph